Gaussian probability models are used in all sorts of places. For instance, in the receiver of your phone, Gaussian noise is added to the received signal. If you look at the scores of everyone on the midterm exam, the distribution of scores has a bell-shaped curve, just like the PDF of a Gaussian. This is not a coincidence. In fact, the central limit theorem is the reason we see Gaussian probability models in so many places. Let's start with a simple example and look at the random variable x, the number of heads in n coin flips. We already know that x is binomial and has PMF, px of x, which is n choose x, p to the x, 1 minus p to the n minus x. And when we look at this PMF, right, we see that for n equals 5, we see something that is kind of a small mountain of probability. As n equals 10, it starts to resemble pretty strongly a bell-shaped curve, although my drawing isn't very good. For n equals 20, the PMF, the bell-shaped curve of the PMF becomes kind of obvious. We know that the binomial random variable x has expected value mu x, which is e of x, which is equal to n times p. We also know that it has variance sigma x squared equal to np 1 minus p. And in these examples, p equals a half. And say for n equals 20, we get mu x equals 10 and sigma x squared, the variance, equals to 10 times 1/4, 2.5. And when we say that the binomial PMF has kind of a bell-shaped curve, we're saying that it's approximated by a Gaussian with the same mean and variance. Our definition of a bell-shaped curve is the curve of the Gaussian PDF. So we can imagine a Gaussian random variable, x, with this mean and variance, and we know that its PMF is 2 pi times sigma squared, sigma x squared, e to the minus x minus mu x squared over 2 sigma squared. And now what we're saying is that this PMF actually is close to this density function in the sense that that this density function is hand-drawn, looks like this bell-shaped curve, and so does the binomial PMF of x. The reason behind this has to do with sums of random variables. In particular, we can define the binomial random variable x to be x1 plus x2 plus xn, where xi is equal to 1 if there's heads on flip I and 0 otherwise. So in fact, the binomial is the sum of n independent Bernoulli random variables corresponding to the n coin flips. And what the central limit theorem says is that sums of independent random variables will begin to resemble Gaussian random variables in the distribution function. Here's the formal statement of the central limit theorem. We start with a sequence of random variables, x1, x2, and so on, that are IID with expected value mu x and variance sigma x squared. And we're interested in the random variable w, n, which is the sum of these xi's. What we'd like to do is to describe the PDF of Wn as n gets large. And the central limit theorem gives us an answer to this But first we have to normalize Wn by subtracting away its expected value and dividing by its standard deviation. In particular, we know that Wn has expected value, which is the sum of the expected values of the xi's. And since they're all the same, it's n times ex, or n times mu x. And similarly, we know that the variance of Wn, because the xi's are independent, is the sum of the variances. So it's n times sigma x squared because the xi's are IID and all the variances are the same. So the central limit theorem is defined in terms of Zn, which is Wn minus its expected value divided by the square root of the variance of Wn. Since this is the same kind of normalization that we did in order to use the phi function to evaluate the Gaussian CDF for arbitrary Gaussian random variables, you should already know that the expected value of Zn is equal to 0, and the variance of Zn is equal to 1. And this is true for all n. However, the Zn's have different distribution functions. That is, we have the sequence Z1, Z2, and so on Zn, and this keeps going. And FZ1 is the CDF of Z1. FZ2 is the CDF of Z2. FZn is the CDF of Zn. And what the theorem says is that even though each of these random variables has the same zero expected value and unit variance, as n gets large, the CDF of Zn is converging to the phi function, the Gaussian CDF. What this says is for very large n, Zn is well approximated by a Gaussian CDF. And for any fixed n, when you say Zn, if Zn were Gaussian, then the difference between Zn and Wn is that Wn subtracts away a constant, the expected value, and it divides by another constant. If Zn is Gaussian, then Wn is Gaussian. And what we conclude from this is that a sum of IID random variables, its CDF converges to a Gaussian CDF, and we like to think of that as saying, oh, the sum of random variables for large n becomes Gaussian. This is the fundamental reason why so many physical situations have Gaussian random variables at their core. So if you take a test with 20 or 30 questions, your score is the sum of 20 or 30 random variables. And if the test is well designed, the questions test different things. These are independent random variables. And so a student's score on the exam can be approximated by a Gaussian random variable. So when 200 students take a midterm exam, the distribution of scores will have a bell-shaped curve because it's easily approximated by a Gaussian distribution. The theorem says that the distribution of the sum converges to a Gaussian distribution as n goes to infinity. But part of what makes the central limit theorem so useful is that for finite n, and not even very large n, a sum of n random variables is nicely approximated by a Gaussian of the same mean and variance. So to see that, let's look at this figure where we have this n uniform 0, 1 random variables. And then what we do is we look at the sum of those. and then we compare that to the PDF of a Gaussian with exactly the same mean and same variance. So for instance, uh, here we have at n equals 1, we have a single uniform 0, 1 random variable. The PDF is this box. And here is the Gaussian with the same mean expected value 1/2 and the identical variance 1/12. So for n equals 1, the approximation with a central limit theorem is not very good. In fact, this isn't surprising that a uniform random variable is not like a Gaussian random variable. However, for n equals 2, the sum of 2, 0, 1 uniform random variables, if you calculate the PDF of that sum, right, you get a triangle PDF, which we highlight here, shown in this slide. And then if you compare that to the Gaussian PDF of the same mean and variance, the dashed line in this plot, they are remarkably similar. Now with 3, 0, 1 uniform random variables, we have the solid line is the PDF of the sum of 3 uniforms, and the dashed line, which you have to kind of look to find, is the Gaussian of the same mean and variance. The approximation is quite good at 3. It's even better at 4. And in fact, kind of a folk theorem is that 601 uniform random variables is indistinguishable from a Gaussian of the same mean and variance. What that means is in many practical settings, you can use a Gaussian approximation even when the sum of random variables is a small sum. 6 or 10 random variables is more than enough to get a good estimate of a probability using a Gaussian approximation. A few slides ago, we observed that a binomial PMF has kind of the bell-shaped curve of the Gaussian. And we said the central limit theorem explains that. And now we kind of understand a little better why. And the reason is because a binomial NP random variable is the sum of n independent Bernoulli random variables. And the theorem says that the CDF of this random variable will converge to a Gaussian CDF. This binomial example reminds us why the central limit theorem is a statement about the convergence of the CDF rather than the PMF or the PDF. In particular, um, like we have our binomial PMF by these bars, and no matter how large n gets, right, these bars are always going to be defined at integer mass points and have 0 probability in between. And you can never say, even when they're dense, that a distribution of mass points is the same as a density function, that they're converging. The convergence really occurs in the CDF function. And so we'll look at that on the next slide. So here we compare the binomial CDF against the Gaussian CDF with the same mean and variance. Specifically, X is binomial NP, so E of X is equal to NP, and the variance of X is equal to NP 1 minus P. Specifically, in this example, we think about kind of fair coin flips and P equals 1/2. So E of X is N over 2, and the variance of X is equal to N over 4. And Specifically, the comparison is against the CDF fx of x. This is the binomial CDF versus the Gaussian CDF with expected value n over 2 and variance n over 4. Since a binomial random variable is discrete, its PMF is always going to be a staircase. So for instance, when n equals 2, it jumps from at 0, and then it has another big jump at 1, and then another jump at 2. And of course, the heights of those jumps are the probability of x taking on the values 0, 1, and 2. And in between, you'll see the Gaussian CDF kind of goes through those jump ups. When n equals 4, there's now 4 jumps, and kind of the biggest jump is getting a little smaller, while the Gaussian CDF kind of tracks this staircase. If we jump ahead to n equals 16, the binomial PMF, the individual jumps keep getting smaller and smaller, and the Gaussian PDF tracks it. But it's important to keep in mind that no matter how large n is, the binomial PMF will always be a staircase, and the Gaussian CDF will always be a smooth, increasing S-shaped function. But what's happening in terms of the convergence of the CDF is that the height of these gaps, like how far the step is either above or below the Gaussian CDF, keeps getting smaller and smaller. So the binomial CDF is always a staircase, but these gaps to the smooth Gaussian CDF get smaller and smaller and go to 0. Because the central limit theorem is a good approximation even for small numbers of random variables, it's useful to define kind of a little more carefully the idea of a central limit theorem approximation. And so the idea here is that you take some random variable wn, the sum of niid x's, each with expected value mu x and variance sigma x squared, but you don't specify any particular distribution for the x's. And we're looking for a good approximation to the probability wn is less than or equal to some value w. In effect, we just want to find a good approximation for the CDF of the random variable wn. And our central limit theorem approximation is to say that this is approximately the phi function evaluated at w minus the expected value of the random variable wn divided by the standard deviation of wn. And this is almost, if wn were Gaussian, wn was Gaussian with this expected value and this standard deviation, then the CLT approximation would be exactly correct. If it's the night before the final exam and you're pressed for time, you probably wish I would stop talking about this theory and just do an example to show you how this would work on the kind of simple exam problem that we could have in a Sakai exam under remote instruction. So here's a simple example to get the hang of the method. So we're going to transmit 1,000,000 bits. And each bit is equally likely to be a 0 or a 1. And so the number of ones, x, the number of ones will be binomial with parameters n is 1 million and p equal to a half. So of course x is the sum of a million Bernoulli random variables. So we're comfortable saying, oh, we should be able to estimate probabilities of x using a central limit theorem approximation. So to do that, we observe that the expected value of x is np, which is 10 to the 6 times a half. It's 500,000. And the variance of x is np1 minus p, which is equal to 1 million divided by 4, 250,000. And very conveniently, if this is the variance of x, the standard deviation is the square root of that, and it's exactly 500. That's why these parameters are chosen to make everything work out super nice. Okay, so the question we're asked here is, what is the probability there are at least 499,000 ones, but not more than 501,000 ones? So we're asking, let me go back to my normal ink color. We're asking what is the probability that x is between 499,000 and 501,000. So what we do here is we, wait a minute, go back to the right page. We write this by subtracting away the expected value and dividing by the standard deviation to put it in a normalized expression, a zero mean unit variance variable. So we take 499,000, we subtract away the expected value, 500,000, divide by the standard deviation, 500. That's less than or equal to x minus 500,000 divided by the standard deviation 500, less than or equal to 501,000 minus 500,000 divided by the standard deviation. So of course you can see that this probability that x is between 499,000 and 501,000 is exactly the same as this probability that the zero mean version of x and divided by standard deviation unit variance version is between here and here. So this is the zero mean unit variance C that we use for the central limit theorem. And particularly the way the approximation works is that we assume that Z has CDF, probably Z is less than or equal to Z. That's exactly phi of Z, the CDF of the zero mean unit variance Gaussian. So now our probability becomes, it's the probability that Z is between -2 and 2, and that's equal to, of course, phi of 2 minus phi of -2, which can be simplified to 2 phi of 2 minus 1. If you get out your phi table and look up phi of 2 or peek ahead to the next slide, you'll see that this is about 0.95. If you wanted to do this calculation exactly, you'd first have to write down the PMF of x, which is n choose x, p to the x, 1 minus p to the n minus x. But since p equals 1 minus p equals a half, this becomes 1 half to the n times n choose x. And now you would have to do the sum to calculate this p of a. You'd have to sum from x equals 499,000 to 501,000 of this PMF of x, 1/2 to the n, which is 10 to the 6th, times 10 to the 6th choose x. And of course, you can factor out the 1/2 to the n, so it's 2 to the minus 1 million times the sum x equals 499,000 to 501,000, 10 to the 6th choose x. And the problem is that this is actually a pretty difficult calculation for any ordinary calculator, or even maybe laptop computer you have. But if you actually do the calculation, you'll get an answer, which is 0.9545. And if you go back and look at the central limit theorem approximation, uh, it was 0.95, but if you actually look at more terms in the phi table, you'll find this answer is actually 9.9544. They're pretty darn close. If you can do this calculation on your own, then you're probably all set for any final exam questions that use the central limit theorem approximation to estimate some probability. So let's stop this segment of the lecture here, and we'll do some more complicated examples in the next part.